some more information for finding the tension T1 and T2. Okay, so I will put some numbers so it's kind of a little bit easier. Let's say this value is 3 and this value is 2 and 2. Okay, so the first thing that you did, and you did a good job, let's call that, I will call that, I think there's an angle on the bottom, alpha B and alpha C. Okay, so after you find alpha B and alpha C with those distances, the 3, the 2, and so we have, if we look at alpha, let's do it together. We have tangent alpha B that is equal to the opposite side, so 3 divided by 2, and we will have tangent alpha C that is equal to opposite side 3 divided by the adjacent side divided by 4. Okay, you can use that. You can also use, if you prefer, that will be exactly the same value. You can use the Pythagorean theorem. So if b equal 3 and a equal 2, this distance there will be 3 square plus 2 square, right? And this distance L2 will be 3 square plus 4 square. Okay, so instead of using the angle alpha b, you can use the 3 divided by the value L1, that is 3 square plus 2 square, or you can use the 3 divided by the square roots of 3 square plus 4 square. Okay, so that's the two options to find. What I'm looking to find here is I'm looking to find the complement of, let me try another color, the complement of T1, but on X, this one for the moment, and the complement of T2, same thing on Y, this one, the T2Y, and this one, the T1X. So this is the clue to find the first equation that will be your sum of the moment about A equal 0. That will give you the T1Y times the distance 2, and it's going up, so it's plus the T2Y times the distance 4, and minus the force F times the distance 4 equals 0. So that will be your first equation. And again, to find the T1Y and the T2Y, use either angle alpha B or this complement on the Y, or alpha C and this complement on the Y for T2Y. Okay, so that's for your first steps. You have this equation. Now what we have is that we have two unknown. We have T1 and T2, and just one equation. So second equation, we will use a deformation of the two cables. And the formula for the deformations with the little delta, so this elongation, we have the delta equal F times the L0 divided by the area times the Young modulus. So we will have the delta 1 and the delta 2 equal F. So let me change that with the exact value. That would be T1, the force in the cable 1, times L1, the initial length of the cable 1, and this one will be equal to T2 times L2 and divided by the area times E. Okay, so that will be the elongation of the cable. But now those little elongation, if we look at our cable, so I will read you oops, this one that was the beam. Let me put it a little bit lower. I want to explain you something there. Okay, so that was the beam, and let's say we look at the L2. So that was the L2 at the beginning. Now my beam is kind of rotating like this, okay? And we have the new L2 plus delta 2, little delta 2. And this is my first distance L2, and this is my delta 2 over there, okay? And we have the same thing for the L1. Okay, L1 was there, and now L1 turn, and we have, oops, I need to put a new, we have the L1 and the delta 1 over there, okay? Oops, the little delta 1. And we don't know the link right away between the delta 1 and the delta 2, Okay, those little delta, this little elongation of the cable, we don't know that. Okay, but what we know is if we look at this similar triangular rules, we know that it was a distance, there was a distance 2 and there was a distance 4. So we know that the distance 2 divided by 4 equal the delta B divided by the delta C. Okay, that the similar triangle rules because delta B and delta C are parallel. So we have this information there. So let me put that there. So we have 2 divided by 4 equal the delta B divided by delta C. Delta B, it's same thing than delta for the cable 1 and delta for the cable 2. Okay, I use kind of different notation. But notice like uppercase delta, this is not this little delta over there. Now, if we look closer to my little delta and my bigger delta, okay, again, this distance all the way to there, it's L2, like at an angle, and this one is a little delta 2. We have a right angle there, so we have this angle alpha, and this angle alpha there. And we can see this uppercase delta C and this lowercase delta C. And if we look at that triangle, we can see that sine alpha C equal opposite the delta 2 divided by the delta C, that is also my delta 2, my uppercase delta 2. Okay, so here we are starting with that equation. Okay, let's start with that equation. This one. Okay, so we have 1/2 equal delta 1 divided by delta 2. Let's rewrite that. I switch my 2 over to the right, so we have delta 2 equal delta 1 equal 2 delta 1 equal 2 delta 1. Okay. Now if I use this equation there, okay, I have sine alpha of the angle C times delta C, that is also my delta 2. Okay, I know it's confusing. Let's see delta 2 and delta B. Okay, let's do this way. Sine alpha C times delta C equal the little delta 2. I'm coming back with the delta 2. Is that C? Yeah, C is the delta 2. Did I mess up that? I should not change those dimensions, this notation, sorry. But anyway, so my delta C there, it's equal to my delta 2 divided by sine of the angle alpha C. So you see now I'm grabbing that and I can put it inside this equation there. Okay, so we do have delta C, that's little delta C divided by sine of the angle alpha C equal to delta B sine of the angle alpha C, right? Yes, we are almost there. Now, I know I use colors all the time. That's little delta. I can go grab those formula there. So I have, so that the C is the 2. So we have T2 times L2 divided by A times E times sine alpha at the point C. That is equal to 2 at B, that's T1 times L1 divided by A times E times sine alpha. That's a B there. That's a B, alpha B. Okay. The area of the cables, we will take the same. The module jung, we will take the same materials. So we ended up having an equation that looks like, let's write that, L2 divided by sine alpha C times T2. I will switch that on the other side. So minus 2 times L, oh, that's a L1. Why did I put a 1? Stop. I know you cannot stop it, but L1 divided by sine alpha B times T1 equals 0. And this is our second equation with T1 and T2 that we will use. We don't see that. That's our second equation. So now we have one equation for T1, T2 from the equation of moments. That was this one there. Oops, let's stop there. And we have that second equation there. Here we go. So you can use, do not try substitution. please, please, please do not try substitution. Use instead the matrix system. Pretty easy to plug that two times, plug that, and solve for it. Okay, I hope that that makes sense. One of the formula also for this problem that you need to use is your sigma, the stress equal the force divided by the area when you need to find the area. Remember that you have your coefficient of safety, so plan that your area can hold 3 times the force, or like that the maximum stress, the yield strength is 3 times lower, okay? And do 2 steps at a time, so you find your area equal the force divided by the stress, and your area equal PR square, so you can use that to find R, and after that to find the diameter. Do more steps. It's better to do more steps than less, okay? Otherwise um, it's kind of like, it's not that it's confusing, but it's like you're missing some information when we want to come back on what you did. So I hope that makes sense for that problem. I don't have a nice end picture because I kind of wrote everything there. Another advice: make a nice free bar diagram. If your free bar diagram is not well made, you will have mistakes in the distances for the moment, which complement to use, and etc. etc. So that's it for my little video. Hope everything is getting a little bit more clearer for you.